This is where we ended, looking at the conservation of energy, where the work done by my external load, P, to displace a structure, big delta, is equal to the work of the internal load, the strain energy that force causes, with my internal load N, my internal displacement delta, baby delta. And if I take the area under the two curves, because it's a linear relationship, because we have we're assuming a linear elastic material and response, the area under those two curves should be equal to each other. So now I can use that relationship that I just determined to develop the approach called virtual work. So let's say I have this bar that's on an angle, and I apply a horizontal load P, and it results in my bar being, this joint being deflected or displaced delta. Well, I can determine my internal force in that member N, right? That is caused by that load P that I applied. And then I have my bar elongating little baby delta. Which contributes to the deflection of that support, big delta. If I have my little chart, my work done by that external load is the area under this curve. UE equals 1/2 P times big delta. Work of my internal load UI is equal to 1/2 my internal force times that elongation of the bar, delta, and UI I also figured out is equal to n squared, oopsies, 1/2, sorry, 1/2 n squared L over AE that I just determined using the conservation of energy. So that means if I want to figure out big delta, I have to know have to determine the internal forces in my bars. So I'm going to develop two systems. One is my actual system, my actual structure where I have my load P causing a displacement of this support or this joint, big delta, which leads to an internal load on that bar N and an elongation of the bar little delta. And the external work associated with my applying that P is this, right? My internal work is this triangle, this area. And now I decided that I really want to know what that value, how much it deflects, right? So I'm going to apply a unit load in direction of my unknown displacement. So I have this deflection that's going horizontally to the right, I think. I'm assuming it's going horizontally to the right. And I'm going to apply a unit load P1 or P prime. Now, just as an aside, everything a prime. Everything with my virtual system, I'm going to put a prime on it. So I have my P prime, which is my unit load. P prime, and it's going to cause a displacement of my virtual system delta prime. And I'm going to have an internal load on that member N prime and an elongation delta prime. Right? And again, I can chart the work of the load. Right? This is the external workload, UE prime. And I have my internal virtual work strain energy, UI prime. Okay. So I have, right, my internal virtual system, internal, external virtual system. Trying to keep colors here. My external real system having an energy right there. And my internal real system causing internal energy. So now what if I take my real and my virtual system and I add them together? And I'm going to apply right? Let's see. P prime plus P, and it's going to cause deflection big delta prime plus delta, right? I got P prime, big delta prime, P, big delta. And I'm going to, that's going to cause internal loads N prime plus N and an elongation in that bar, baby delta prime plus baby delta. Right? N plus N prime and delta plus delta, baby delta plus baby delta prime. Let's say I apply the P prime first. So, let's see. All right, I'm going along here. I add P prime, which causes a deflection. Big delta prime. Then I continue and I add P, so this value here, right? This is P, so this value here, the total is P plus P prime. Let's see, this height here, right, is P. Oopsies, P prime. So that my total applied load is P plus P prime. And it's causing a deflection of delta prime plus delta. And that little triangle here, my virtual system, that's my energy associated with my virtual system. The external energy associated with my real system, due to the external load. And then I have this extra little bit, this extra rectangle right here, that I'm going to call UE star. I can do the same thing if I look at the internal energy, right? I apply P prime and it causes an internal load of N prime and an elongation of delta prime. And then I apply P, causing an internal load of N and an additional elongation delta, so that my total at the end is baby delta prime plus delta, and my total internal load is N prime plus N. My internal energy associated with my virtual load, right? UI prime. My internal load due to my real system, UI, and then there's this extra little UI there. got. Let's see. External energy. Virtually. P. Right? P delta. P prime. Big delta prime. And this extra little bit. UE star. I need like another color. I don't know what. Orange. That's fine. And then my virtual system causing these internal energy, and my real system causing the blue internal energy, and the extra little bit UI star. Right? Now, this is where I'm going to need some extra colors. Should I start with orange? The total external load energy, the work caused by that external load, needs to be equal to the total strain energy, right? These two big triangles need to be equal to each other. So let's see. I need my UE prime plus my UE, those are those two triangles, plus UE star needs to be equal to UI prime plus oopsies, UI prime plus UI plus UI star, right? These three values are equal to this triangle and the other three values are equal to this triangle, all right? Now we already established that UE prime is equal to UI prime. The external work in my virtual system is equal to the internal strain energy in the virtual system. My external work in the real system is equal to my internal work in the real system. So I gotta cross some stuff out, right? Green is equal to purple, red is equal to blue. Established. That looks terrible. So that means, therefore, UE star is equal to UI star. Now what are the dimensions of those two rectangles? All right. UE has a height of P prime and a width of big delta. UI star has a height of N prime and a width of baby delta. So that means P prime times delta is equal to N prime times baby delta. If P prime is equal to 1, it's a unit load. Actually, hold on. That means let's see. All right, this is the external virtual load. This is the external real displacement. This is the internal virtual load or virtual force. And this is my internal real deformation, I guess. Right. Maybe we call that internal virtual force. If P prime is equal to 1 because it's a unit load. Then my actual displacement delta is equal to the internal virtual force times the internal real deformation of that member. Or if I have multiple members, I'm going to sum the virtual forces times the deformations. So that's the derivation of how virtual work works. Now, if you're wondering what the UE star, why there's this extra, I should have said it earlier and I didn't. If you're wondering what this extra rectangle is, like we had the two triangles from applying our loads, but now we have this extra rectangle. And the extra rectangle, the stars, right? UE star and UI star. They represent the work done by the load that's already applied due to the additional deformation applied by the second load. So it's already there. It's just now it's moving with the load, right? And that's why it's a rectangle, force times displacement, right? The force isn't changing anymore. P prime isn't changing, and N prime isn't changing, but they're moving with the additional load delta or baby delta. So that's why it's a rectangle, force times displacement, what you learned earlier what work was. Okay. So how do I apply virtual work? So I have an unknown displacement, delta, to determine internal virtual load N and internal real deformation baby delta. So I'm gonna have so here's the procedure. I'm gonna have two different systems. My real system where I apply real external loads. To the structure and determine my internal displacements that are caused by real internal loads. And then I'm going to draw the exact same structure as a virtual system. Where I apply a unit load external unit load to my structure in the direction of desired, not desired, let's say unknown, in the direction of your unknown displacement. And this unit load could be a force or a moment, and the displacement could be a displacement or a rotation. Right now we're sticking with displacements because we're only in axial members trusses. I'm going to apply an external unit load in the direction of my unknown displacement delta, big delta, and determine my internal loads virtual internal loads N prime due to that unit load I'm going to do that throughout the structure. Similarly, I should say it here, due to determine the internal real deformations due to the real internal loads and do it throughout the structure. Right, you do it for every member within the structure. And then to determine delta, I just take a sum of those internal virtual loads times internal real deformations. And that is the basis for how virtual work works. Okay. Next, we're going to apply it to a truss, but I'm going to pause.